Hello, this is Jared Niemi with a mini lecture on p-values. And more specifically, we're really just talking about a randomization p-value here. Alright, so to first talk about the p-values are used to talk about the plausibility of hypotheses, scientific hypotheses about the way that the world works. And in order to create a p-value, we need two hypotheses, one a null hypothesis and the other is an alternative hypothesis. And I find it convenient to think about the alternative hypothesis first because typically this is the way that we actually think the world is working. Right? That is, we specify the alternative as the way that we think the world is working, and then the null hypothesis is essentially the opposite of that. And usually this refers to a simpler state of affairs. So this might be what is pre-existing and is thought about how the world works, and you think the world is a little more complicated than that, and that there's this additional piece of complexity in the world, and that is what you put into the alternative hypothesis. Alright, so coinciding with these hypotheses, we have we have two main types of hypotheses, two-sided hypotheses or one-sided hypotheses, and those one-sided, we'll see in a second, can be broken down into two different categories. And typically what we're going to do is to define a parameter in a model that describes the differences between these two hypotheses. So as an example, you might say that this parameter delta is the expected difference in the response between two groups, group A and group B. And so a two-sided hypothesis might say that the null says we don't think there's any difference between these two groups in terms of the response, the expected difference. So we think that delta is 0. That's the null hypothesis, and the alternative hypothesis is saying, okay, well, we don't believe the world is that simple. We think there's actually some difference between these two groups, and so our alternative just says that the difference is not 0. So that would be an example of a two-sided hypothesis. A one-sided hypothesis says that delta is only going in one direction. So in the first case, our alternative says that delta is greater than 0, and in a different case, we say that delta is less than 0. Right, so this is a hypothesis that you set up before you collect the data, really. All right, so you specify your hypothesis, and now you go out and you collect your data, and you say, we want to make some statement about which hypothesis better represents the world based on the data that we have. All right, and so in order to do that, we're going to calculate a p-value. A couple definitions before we get to p-value. The first is that we need to know what a statistic is. A statistic is just some numerical quantity that you calculate from the data. And in order to get a p-value, we're going to use something called a test statistic, and this is just a very specific statistic that's used to measure the plausibility of these two hypotheses. And in the example that we have, this test statistic is going to relate to delta. Alright, so a p-value then is the probability of observing a test statistic as or more extreme than that observed if the null hypothesis is true. So this p-value is calculated with the assumption that the null hypothesis is in fact true. We're going to talk more about what as or more extreme means on the next slide when we talk about a particular example. In order to get at this p-value, we need this notion of the sampling distribution of a test statistic. So this is the distribution of the test statistic if the null hypothesis is true. So basically we want to understand if the null hypothesis is true, here's the general variability that we would see in that test statistic, and if the test statistic we actually saw in our particular data set is way outside of that distribution, then we would say it's unlikely that the null hypothesis gave rise to this particular value of the test statistic. Alright, so let's give a particular example. So here's an example where we're going to have two different groups, and our null hypothesis is that there's no difference in the response between these two groups. That is, the treatment that we have has no effect. Alright, so let's imagine that we had 4 individuals. We're just going to label them A, B, C, and D, and that we actually had this response 1, 2, 3, and 4 for individuals A through D respectively. And now we, let's say, randomly assigned treatments to the 4 individuals. Right, we would have done this before we actually observed the response. But in this case, what we randomly assigned is that we randomly assigned individuals A and B to this treatment negative, and C and D to the treatment positive. Alright, so this is one way that the treatments could have been assigned, but they could have been assigned in a different way, right? Because we randomly assigned the treatments. One way that they could have been randomly assigned is that A and C had the negative treatment and B and D had the positive treatment. And we can just enumerate the different scenarios that we have for the way the randomization could have gone. If we want to keep two individuals in both groups, then there are 6 different ways that the randomization scheme could have gone. Alright, so now if the treatment actually has no effect, that is if the null hypothesis is true, then the treatment, this bottom part, has no effect on the response that we actually saw. And so we would think that these would be the responses that we would have seen regardless of the treatment that was assigned. And so what we're going to do is we're going to calculate the distribution of the test statistic under these 6 different randomization scenarios. In this case, we expect there's no difference between the two groups, and so our test statistic is going to be the difference in the averages of the two groups. Alright, so for example, in the randomization scenario that we actually observed, we're going to take the average of the individuals in the negative group, that is A and B. So the average there is 1.5. And we're going to take the average of the individuals in the plus group, that's 3.5. And we're going to subtract them. In this case, we're going to subtract the plus, well, we're going to subtract the minus from the plus. Alright, so in that case it's 0, right? 3.5, sorry, in that case it's 2. 3.5 minus 1.5. And now we can do the same thing for this scenario too. So if this had occurred, what we would have expected to see is that we have the plus group is 2 and 4, so that average is 3, minus the average of 1 and 3, which is 2, so 3 minus 2 is 1, so we would expect to see a 1. And now we're going to go ahead and calculate that same quantity for all 6 different scenarios. Alright, and so these are the values that if the null hypothesis is true, that our test statistic, again the test statistic is the difference of the averages in the two groups, could have seen. So this is the sampling distribution of the test statistic right here. Right, just to reiterate that, this is the sampling distribution because we're just looking at this randomization of the treatment. This is also called the randomization distribution of the test statistic. And it's uniform over these 6 numbers. That is, each of these numbers had probability of 1/6 of giving rise to the test statistic that we actually saw, if the null hypothesis is true. Alright, but we actually saw this test statistic. So then the question is, well, how much evidence is there against the null hypothesis when that's the test statistic we actually saw, and these are the 6 that we could have seen? Well, that answer depends on what the hypothesis was that you set up ahead of time. Alright, so if delta now here is the true difference between the treatments, then if you set up the two-sided hypothesis, that is that the null hypothesis says there's no difference, and the alternative says that there is a difference, but we don't know which way it was, then the question is we need to calculate something that's as or more extreme. And in this case, what we mean by that is that it's more toward the alternative hypothesis. Right? So the null hypothesis says there's no difference, so anything farther away from 0 is extreme. Right? So what we actually observed was 2, and 2 is 2 units away from 0, but minus 2 is also 2 units away from 0. So those are the 2 quantities that are as or more extreme than the test statistic we actually observed. Right? So these are the 2 possibilities that are as or more extreme, and there were 6 total possibilities, so our p-value is 2/6, right, which is just 1/3. Now if instead we had a one-sided hypothesis instead of the two-sided hypothesis, and in this case we had the one-sided hypothesis where the alternative says that we expect that delta is going to be greater than 0. We expect that the plus group is going to be larger than the minus group. Then being positive and farther away from 0 is extreme. Again, by extreme here we mean that it is giving more support to the alternative hypothesis. Well, in this case, the only thing that's as or more extreme than 2 is just 2 itself. There's nothing more extreme. There's nothing on this side of the line over here that we could have possibly seen for our test statistic. So in this case, we have one time, right? We had one thing out of 6 that was as or more extreme than that what we actually observed. So the p-value here is 1/6. The opposite scenario is that we had a one-sided hypothesis, but we thought that delta was going to be less than 0. In this case, being extreme is being negative and farther away than 0, than 2, right? Well, nothing is farther, well, everything is farther away than 2 and toward the negative sign. So in this case, we observed a 2 and everything else is more extreme. So our p-value is 6/6, which is just 1. Alright, so this p-value is giving the evidence against our null hypothesis, which depends on what our hypothesis was. And the key thing here is that smaller values give more evidence against the null hypothesis. Right, so if this is our null hypothesis here, then this is basically no support for our alternative hypothesis, so we fail to reject the null hypothesis in this scenario. In these two scenarios, well, this is as extreme as we could have possibly gotten as 1/6. So how much weight does that say about our null hypothesis? It's hard to say. It basically says we should probably get a larger study, because 1/6 isn't a very small p-value. Alright, so in summary, this idea of this randomization p-value, this randomization distribution for the p-value, provides a gold standard. Right, this might be the way that we would like to calculate the p-value. The problem is going to be that with larger sample size, it's basically going to be infeasible to calculate all the different possible ways that we could have randomized the treatments to the experimental units. And the second thing is that small p-values provide evidence against the null hypothesis. Thank you.